Welcome students. Today we will discuss kinematics. Kinematics is the branch of physics that deals with the motion of objects without referring to the causes of motion. We want to study what are the causes behind this motion. We will only concentrate on various aspects of motion. So in this branch we will study how a body moves in various ways. Kinematics can be further classified into one-dimensional and two-dimensional. In one-dimensional motion, the object is moving only in one direction with respect to time. Its displacement will be only in a single direction, whereas in two-dimensional motion, simultaneously the object covers displacements in two directions. That's why this is called two-dimensional motion. Of course, there is three-dimensional motion which we generally don't require to cover in this level. Only one-dimensional and two-dimensional motion we will study in this chapter presently. Now, before going into the details of these things, first let us study only one-dimensional motion or 1D motion. One-dimensional motion is, as I told you, is the motion of an object only in a single direction with respect to time. Now, before going further into this, let us start with basics. You already know what is meant by distance traveled, displacement, velocity, etc. I am not going into the basic definitions of those things. I will just straight away go for in this one-dimensional motion also there are two types. A, bodies moving with uniform velocity, with constant velocity. Constant velocity, that means their velocity will not change with time, they won't have any acceleration. So that is one kind of motion. Second kind of motion is bodies moving with uniform acceleration. The body is moving with uniform acceleration. These are the main aspects in this one-dimensional motion. Of course, bodies may be moving with non-uniform acceleration, but that aspect is negligible. If at all possible, we will mention in one or two examples. But basically, these are the two things which are more important to be covered. Now, let us study this A and B part in detail. Body is moving with constant velocity. In this aspect, body is moving with constant velocity. In this aspect, actually velocity remains constant during the given period of motion of the body. For example, a body started at the point A and reached the point B. If its velocity remains constant throughout the motion, then it comes under the constant or uniform motion of the body. In this case, displacement is equal to velocity into time. Students always confuse in various cases of motion. Remember, when a body is moving with constant velocity during a particular time t, then displacement in that time period will be equal to velocity into time. Simply this will give you displacement if it is moving with uniform velocity. Now, here also there are different aspects which we can study. With uniform velocity also, what can happen is the body may move with one value of uniform velocity for a particular displacement, and then another value of uniform velocity next displacement, and so on. For example, a body covers displacement S1 in a time T1 and S2 in a time T2, S3 in a time T3, etc. So, the body covers S1 in time T1, started from this point and covered S2 in time T2 and covered S3 in time T3. So, see here the body covered successively S1, S2, S3 in successive intervals of time T1, T2, T3. Now here total displacement will be equal to S1 plus S2 plus S3 and total time taken is T1 plus T2 plus T3. Now if you take velocity in this period, in this period is V1, velocity in this period is V2, velocity in this period is V3, then if time is not given, during the first S1 displacement, the particle has velocity V1. During the second S2 displacement, it has velocity V2. In the next S3 displacement, it has velocity V3. How to find the average velocity for the whole motion? Simply, you go for the basic definition of average velocity. Average velocity is equal to total displacement by total time taken. So use that relation only here also. Even if the extension is for S4, S5, S6 also, you can apply the same relation. So here if you apply this relation, what we will get? Average velocity, which can be denoted as V bar, is equal to total displacement by total time is the basic definition for average velocity. Total displacement is S1 plus S2 plus S3 by total time taken means during this period it is moving with uniform velocity V1. Therefore, time taken will be S is equal to V1 T1. So, T1 is equal to S by V1. So, time taken for this motion is only S by V1. For this motion will be S2 by V2, S1 by V1 and here S2 by V2, here S3 by V3. Timings are S1 by V1, S2 by V2, S3 by V3. So, total time taken means T1 plus T2 plus T3 means S1 by V1 plus S2 by V2 plus S3 by V3. So, here we got the average velocity is equal to total displacement by total time taken, which is like this. So, this is the general relation to find average velocity in this type of cases. Suppose if the three displacements are equal, this is S, this is also S, this is also S. Then first 1/3 of the displacement it covered with a velocity V1, second 1/3 with a velocity V2, third 1/3 with a velocity V3. Then average velocity will be equal to S plus S plus S by S by V1 plus S by V2 plus S by V3, which will be equal to 3S by S into 1 by V1 plus 1 by V2 plus 1 by V3. So, what you will get here is average velocity is equal to 3 V1 V2 V3 by V1 V2 plus V2 V3 plus V3 V1. Average velocity here will be equal to 3 V1 V2 V3 by V1 V2 plus V2 V3 plus V3 V1. This will give you the average velocity for the total motion here. Similarly, if it travels only two displacements, first half of the displacement with velocity V1, second half of the displacement with velocity V2, same relation will help you to find the average velocity, which is nothing but average velocity is equal to S plus S total displacement by total time taken. This will give you this one 2 V1 V2 by V1 plus V2. So, this is the average velocity for the motion here. First half of the displacement with velocity V1, second half of the displacement with velocity V2. Therefore, average velocity for the total motion will be equal to 2 V1 V2 by V1 plus V2. If there are three intervals of equal displacements, then average velocity is equal to V1 V2, 3 V1 V2 V3 by this one. Even if four equal intervals of displacements are given, S with velocity V1, S with velocity V2, etc., S with velocity V3, S with velocity V4, like that, you can always use the same method, total displacement by total time taken, you will get the average velocity, which is as simple as this. Now, let us take another case. Suppose a particle travels with velocity V1 for an interval of time T1, and then it travels with velocity V2 for an interval of time T2, and then with velocity v3 for an interval of time t3. In this case, how to find the average velocity? Here also the definition is same. Average velocity is equal to total displacement by total time taken. So total displacement here will be equal to S1 is V1 T1, S2 is V2 T2, S3 is V3 T3. So total displacement is S1 is V1 T1 plus S2 is V2 T2 plus S3 is V3 T3 by total time taken is T1 plus T2 plus T3. This will give you the average velocity when the particle is moving with velocity v1 for the first interval of time t1, next with time interval t2, next with time interval t3. Similarly, if intervals are equal, you have to substitute in place of t1, t2, t3 only t value, then you will get the average velocity. For example, in the first 1/3 of equal interval, if it travels with velocity v1, in the first t seconds v1, in the next t seconds with velocity v2, in the last t seconds with velocity v3, then what is the average velocity? Means simply what you have to write is v1t plus v2t plus v3t by t plus t plus t. That means what you will get here is v1 plus v2 plus v3 by 3. This is the average velocity. If two equal intervals are only taken, you will get v1 plus v2 by 2. If there are unequal intervals, means v1 plus v2 plus v3 plus and so on vn by n. That will give you the average velocity. Now let us come to next to B part of the one-dimensional motion, where acceleration is also considered. Acceleration is taken, but uniform acceleration is considered. It is not non-uniform, remember that. So when a body is moving with uniform acceleration, if a body is moving with uniform acceleration is present means velocity keeps on changing. Therefore, you have come to the basic equations of kinematics with uniform acceleration, which are these things only. V is equal to u plus at and v square minus e square is equal to 2as and s is equal to ut plus half at square and Sn is equal to u plus a into n minus half. So these are the basic equations of one-dimensional uniformly accelerated motion. They can be applied to any one-dimensional motion, whether it is a body moving in a straight line like this, or a body falling freely, or a body projected upwards. In all these cases, we can apply these equations. While applying these equations, always remember you should use proper sign convention. Otherwise, you will get wrong results. Proper sign convention should be adopted. That means always choose the initial direction in which the velocity is given. In that direction, you take all quantities positive. For the sign convention, most important point is you assign positive sign to the initial direction of motion and negative sign for all opposite quantities. For example, if a body is projected upwards from the top of a tower with a velocity u, if a body is projected upwards from the top of a tower upwards, then initial velocity is upwards, initial motion is upwards. So all upward quantities you should take positive, downward quantities you should take negative. That means what happens here is the body reaches the ground, so its displacement is opposite to initial direction of motion. So here you will have displacement is negative. That means if this height is h will be negative. You have to write minus h is equal to ut, and g is also downwards, so minus half gt square. So if you use the proper sign convention, you are getting the equation of motion for a body projected vertically upwards from the top of a tower of height h. So it is very easy to frame the equations if you remember this sign convention. Now, in all these equations, remember one more point. These one-dimensional kinematic equations, if you observe, first one third one, fourth one are called vector equations. They can be represented in vector form also, whereas this is called a scalar equation. This is the only equation which is a scalar equation, because here v dot v is there, u dot u is there, a dot s is there. Automatically all these quantities will become scalars. So this is called scalar equation. These three are called vector equations. So sometimes you can also see the equation like this, which is 100% correct. So similarly you can write this and this also in vector form, but this is in scalar form only. Remember that. In objectives they may ask you whether this equation is scalar equation or vector equation, whether this is scalar equation or vector equation, like that. Remember that. Now these normal equations of motion for uniformly accelerated body can be applied to any unidimensional or unidirectional motion. For example, you take a body projected, dropped freely from the top of a tower. If a body is dropped freely from the top of a tower of height h, the time taken for it to reach the ground, h is equal to, normal equation is s is equal to ut plus half at square. This is the kinematic equation. Now you have to apply this equation here also, because this is also one dimensional motion, and here only thing is its displacement is height only, so s is replaced by h. Because it is freely falling body, you have initial velocity 0, so 0 into t is 0, this will become 0, plus half into g is acceleration due to gravity. So h is equal to half gt square is the equation you have to use whenever a body is freely falling. Similarly, you have to use v is equal to gt and v square is equal to 2gh. This is the set of equations which you can use for a body which is freely dropped. So these equations, even you can use hn is equal to g into n minus half. So this set of equations are always for a freely falling body. Remember that. From these equations you can learn so many things if you keep on applying. I will tell you one or two. See here, h is equal to half gt square if you take, in the first second how much displacement it will have. h1 is equal to, first 1 second means t equal to 1 second. In the first 1 second it will have half g into 1 square, that is g by 2. Its displacement will equal to g by 2. In the first 2 seconds, it will have a displacement of h. Suppose if this total displacement is concerned, is taken, then it would be equal to half, h is equal to half g into 2 square, that would be equal to 2g. But in the first second it travelled a distance g by 2. So in the next second it travelled a distance equal to, h2 is equal to 2g minus g by 2, which is 3g by 2. So h2 is equal to 3g by 2. You can find h3 is equal to 5g by 2, h4 is equal to 7g by 2, like that. That means what is happening here, a freely falling body covers a distance g by 2 in the first second, 3g by 2 in the next second, 5g by 2 in the next second, 7g by 2 in the next. So in consecutive seconds the ratio of displacements will be equal to g by 2 is to 3g by 2 is to 5g by 2 is to 7g by 2, means 1 is to 3 is to 5 is to 7 and so on. For a freely falling body, this is the case. Remember, this is also applicable for a body moving in a straight line on a horizontal road starting from rest with uniform acceleration. The same result is applicable for a body moving with uniform acceleration and starting from rest. That is condition required. Starting from rest, if it moves with uniform acceleration, ratio of displacements in consecutive time intervals will be same. Suppose if you are given, a body started in a horizontal path from rest with uniform acceleration. In the first t seconds it traveled a distance x. In the next t seconds, how much distance it will travel means simply you can say 3x. You need not do anything, because this qualifies for the case of freely falling body only. Now, if a body is projected vertically upwards with initial velocity u, here also we can apply one-dimensional equations with a small change. Here initial velocity is u upwards, g is downwards. Initially, as it is moving upwards, its displacement is also upwards. So, by applying proper sign conventions, we can write the equations of kinematics as h is equal to ut minus half gt square, and v is equal to u minus gt, and h v square minus u square is equal to minus 2gh, and hn is equal to u minus g into n minus half. These are the set of equations which are used for a body projected vertically upwards before reaching the highest point. Remember that. Here there is always some confusion when these equations should be applied for a body projected upwards. As long as it is not reaching the highest point, you can use these equations. Once it reaches the highest point, velocity becomes 0, so that becomes a separate case. Until, as long as it is somewhere here, you can use all these equations. But if it reaches here, automatically velocity becomes 0, and you have to substitute velocity v equal to 0 here. Then automatically what happens, suppose if you take this only, it reaches the maximum height in some time t, then 0 is equal to u minus gt, t is equal to u by g. That means time of ascent, time to reach the maximum height is u by g, which you know already. Similarly, time to come down is also equal to u by g. So, total time of flight for a body projected upwards will be equal to 2u by g, which are familiar to you, these results. So, these are the equations for a body projected upwards. Now, let us take some interesting cases. Suppose this is a tower of height h. This is a tower of height h. A body is dropped from it. From the top of the tower, a body is dropped. Simultaneously, another body is projected upwards with a velocity u. At the same time, a body is projected upwards with a velocity u. They will meet in their path somewhere. Now, by the time they meet, let this body falls a distance x. When they meet, displacement of the body which is dropped from this point is x. During the same time, displacement of the upward projected body will be equal to h minus x. So, this body displaces h minus x, this body displaces x by the time they meet. Now, let us apply equations. This is a freely falling body. So, during suppose time taken to reach from here to here is t, during the same time it also reached here, no? So, let the time is t, x is equal to half gt square is the equation for this. And for this which is projected upwards, h minus x is equal to ut minus half gt square. This is the equation for this one. Now, if you write half gt square is equal to x here, h minus x is equal to ut minus x, because this is equal to x from first equation, x gets cancelled. So, t is equal to h by u. That means time taken for these two bodies to meet is equal to h by u, this total height by u. You can directly tell from this relation how much time they will take to meet. Now, at what height they will meet means this is the height now, which is equal to h minus x, h is equal to half gt square already we know, and total height we know. Therefore, at what height they will meet means at a height h by x, which is equal to h minus x is half gt square, half g into t is h by u, no? So, t square means h by u square. This is the height where they will meet. Now, similarly, another interesting result is, suppose you project a body vertically upwards with a velocity u. If you project a body vertically upwards with a velocity u, let us suppose it crosses a point P during its path upwards. During its path upwards, it crosses a point P after a time t1 seconds and comes back to the point P after t2 seconds from the beginning only. After t2 seconds, total time taken from here to here is t2 seconds. So, the particle projected vertically upwards crosses the point P in upward journey after t1 seconds and crosses the same point P after t2 seconds in the downward journey. Now, from here to here time taken is t1, from here to here time taken is t2. Now, from here to here, what is the time taken? See, this part has a time equal to t2 minus t1, because this total time is t2, this time is t1, this part has a time t2 minus t1 and this is half of this, therefore, that would be equal to t2 minus t1 by 2. So, time taken from P to the maximum height is this. So, total time taken to reach the maximum height is t1 plus t2 minus t1 by 2, which is equal to t2 minus t1 plus 2t1 by 2, which is equal to t1 plus t2 by. So, total time required to reach the maximum height is this from the ground. Total time of flight of the body is double this, because time of ascent is equal to time of descent. So, total time of flight is equal to t1 plus t2. This is the time of total journey of the body. Now, here if the height of this point is h, we can write h is equal to ut1 minus half gt1 square, because we projected it with the velocity u and it reached a height h after t1 seconds, we can apply this equation. But from the starting after t2 seconds also it is here. So, again we can use the same equation for t2 seconds, h is equal to ut2 minus half g2 square. This is also correct. This is the funny part of the equation, because when it is crossing the point P after t1 seconds, height reached is h only. When it comes back to this point, again height reached is h only. That is why both the equations are correct. So, if you equate these two, and if you simplify it little bit, like this, this gets cancelled. So, u will be equal to half g into t1 plus t2. So, you got the velocity of projection in this case also, which is equal to half g into t1 plus t2. Now, if you substitute this u value here, you will get height also, which is equal to half g t1 t2. Just I am showing some of the derivations to show you how to derive. There can be so many relations which you can derive on your own. I am just showing a few, one or two. This is the way basic equations can give you some of the interesting results. So, in this case, height of the point P is this, velocity of projection is this, total time of flight is t1 plus t2. Now let us come to the two-dimensional motion. Already we discussed the one-dimensional motion basics. Now 2D motion. That means simultaneously the body covers displacement in two directions. Best example is a body projected at an angle theta to the horizontal. If you project a body at an angle theta to the horizontal, it will travel like this. That means simultaneously it is traveling in the horizontal direction as well as in the vertical direction. So displacement in the horizontal direction is like this, displacement in the vertical direction is like this. Suppose you project it at an angle theta here, it reached this point P after some time, then this is the displacement in the horizontal direction, this is the displacement in the vertical direction. So if you consider this as y, this as x, simultaneously the body covered displacement in the x direction, displacement in the y direction. So this is the example for two-dimensional motion. Another example is suppose this is the top of a tower, you project a body horizontally, it travels like this. In this case also what is happening, at any point of time it is having displacement in this direction, horizontal direction, and in this direction. So simultaneously here also there are two displacements in the horizontal and vertical direction. So these are the best examples for two-dimensional motion. So these two examples are in fact called projectile motion. First one is called oblique projectile, second one is called horizontal projectile. Now let us see the relations for oblique and horizontal projectile. Suppose if you project the body at an angle theta to the horizontal with a velocity u, it will reach like this to this point. When the body reaches the same level of projection, the total time is called total time of flight, no, which is equal to 2u sin theta by g. Formulae I am not deriving all because of lack of time, just I am giving you the results. T is equal to 2u sin theta by g is the time taken to reach the same level of elevation from here to here, and the distance travelled in the horizontal direction during the time of flight is called range, which is equal to u square sin 2 theta by g. Now during its projectile motion, during its path, at some point it is at the highest point or at the maximum height. This maximum height is equal to u square sin square theta by 2g. This is the maximum height of the projectile during its motion. Now these are the three important results for oblique projectile: range, maximum height, time of flight. Time taken to reach the maximum height is half of the time of flight, u sin theta by g. Now one more thing here is, this range will be maximum for the given velocity when this value is maximum. Sin 2 theta is maximum when sin 2 theta value is 1, or 2 theta is equal to 90 degrees, or theta is equal to 45 degrees. That means range is maximum when the angle of projection is 45 degrees. Now one more point here to be noticed is, see, u square sin 2 into theta is also equal to u square sin 2 into 180 u square sin 180 minus 2 theta. So what happens here, u square, suppose theta is equal to, angle of projection is theta in the first case, then range is equal to u square sin 2 theta by g. In the second case, let the angle of projection is 90 minus theta, then the range will be equal to how much? See here, range in the second case is equal to u square sine 2 into 90 minus theta by g, which is equal to u square sine 180 minus 2 theta by g. We know that sine of 180 minus any angle is equal to sine of that angle. So, this is simply equal to u square sine 2 theta. From trigonometry you can write. That means range is same for the angles theta and 90 minus theta. So, they are called complementary angles. Theta and 90 minus theta are called complementary angles. For complementary angles there will be same range. So, without changing the range, you can project the body at two different angles. Thereby what happens is you can change the maximum height. So, maximum height can be changed. See, for example, here in the first case, suppose angular projection is theta, it reaches like this. If the angular projection is 90 minus theta, it may reach like this. Range will be same, but maximum heights are not same. So, to create two different heights, two different maximum heights without changing the range, you can use the complementary angles theta and 90 minus theta. Problems will be based on this concept in most of the competitive exams, which is very easy. Now, if you project the body from a height h horizontally with a velocity u, it will travel like this and reach the ground. So, this is called horizontal projectile. From the top of a tower or from some height h, if you project it with velocity u like this, it will reach the ground like this. So, during its path, it also covers displacement in the vertical as well as horizontal directions. The total displacement by the time it touches the ground is called range. And whatever the velocity you give in the horizontal direction, you are not giving any velocity in the vertical direction. Therefore, as far as downward motion is concerned, it is a freely falling body. Horizontal projectile is a freely falling body as far as downward projection is concerned. Therefore, time taken to reach the ground is obtained using this equation only. H is equal to half gt square. So, T is equal to root of 2h by g. So, for a horizontal projectile, time of flight, that means time taken to reach the ground, is independent of velocity of projection. If you increase the velocity, it may reach more horizontal distance, but it will reach the ground at the same time, because time taken is equal to root of 2h by g. Now, during this time only it covered this displacement, no? And what is the velocity in this direction? U. There is no acceleration or retardation in the horizontal direction. Therefore, this u remains constant until the time the particle reaches the ground. Therefore, horizontal displacement by the time it reaches the ground, which is called range, is equal to velocity into time, that is equal to u into root of 2h by g. This is the equation for range in case of horizontal projectile. So, for a horizontal projectile, this is the equation which you should remember, and you should also remember that time of flight is root of 2h by g. Now, in case of any two-dimensional motion other than projectile motion, for example, a particle is moving simultaneously like this. It has a velocity, with a particle is moving in a straight line like this. It started from the point O. By the time it comes to this point, it has displacement x in the x-axis direction, displacement y in the y-axis direction. Just I am discussing a two-dimensional example without referring to any projectile motion or anything. It is moving like this. After some time, it reached this point. During this time, its displacement in the horizontal direction is x, in the vertical direction is y. In that case, net displacement is root of x square plus y square. Similarly, if you can have components of velocity in the x and y directions, net velocity will be equal to root of Vx square plus Vy square. In two-dimensional cases, you can always remember that. Coming back to the projectile motion only, see, if you throw a body with a velocity u at an angle theta, after some time if it reaches the point P, see, continuously the angle is changing. What you have to remember here is angle is continuously changing. Even though you projected the body with an angle theta, this angle with the horizontal is completely changing. At the highest point, in fact, angle becomes 0. That means the projectile becomes horizontal and the angle theta becomes 0. So, what happens here? The angle with which you projected is not remaining constant during its path. It keeps on changing. It first decreases, becomes 0 and then increases. Not only angle, velocity changes. Velocity in the vertical direction changes because of gravity. In the horizontal direction, it will not change. Suppose if you give a velocity u, if you divide this velocity into two components, this component is u cos theta, this component is u sin theta, vertical component is u sin theta. U sin theta keeps on changing because of g, u cos theta remains constant. So, at any instant of time, if you want to find what is the displacement in the horizontal direction for a projectile, what you have to do is x is equal to u cos theta into t, because there is no acceleration or retardation. In the vertical direction, if you want to find displacement at any instant, y is equal to u sin theta into t minus half gt square. This will give you displacement in the vertical direction. Net displacement, if you want, you have to apply this formula. Similarly, velocity in the horizontal direction is this only, no change. Velocity in the vertical direction, Vy is equal to u sin theta minus gt. Because initial velocity in the vertical direction is this, acceleration is minus g, therefore, v equal to u plus at formula only we applied, which gives us u sin theta minus gt. So, net velocity is always equal to Vx square plus Vy square. At any instant of time, projectile's velocity means net velocity, remember that. Projectile, if you are asked to find what is the velocity of a projectile at any point, that means he is asking this only, which is equal to root of u cos theta whole square plus u sin theta minus gt whole square. This will give you net velocity during the at any given point. One more thing which is asked in this projectile motion is, what is the angle made by the projectile at any instant of time? At any instant of time, remember that tan theta is equal to, suppose here if you take, if this is theta, in this direction velocity is Vx, in this direction velocity is Vy. So, tan theta is equal to Vy by Vx. That means u sin theta minus gt by u cos theta. That means you can get the angle of projection by simply writing this relation. Tan theta is equal to, actually this can be written as alpha, tan alpha is equal to u sin theta minus gt by u cos theta. This will give you at any time, at any point, what is the angle made by the projectile with the horizontal. Okay, tomorrow we will continue by doing some numericals in kinematics. Thank you.